I guess this is right, isn't it?
It's
Yes.
a good, yeah.
Okay, so I'm ready when you are ready. And if you need to tell me something, shout.
Sounds
I
perfect.
think we can start. We're already 3 minutes late.
Yes.
So good morning. Good morning. I'm tired. Good afternoon, everyone, and welcome to this session dealing with 10 years of operation synergies with Earth observation missions. It is a real pleasure for me to co-share this session with my colleague Tanya Casal, coordinator of Polar Campaign, who is apparently on leave today at Tahiti, according to her background.
Yes, it's beautiful outside.
So we have 5 exciting talks this afternoon covering a wide spectrum of topics and showcasing key components of an operating mission such as CryoSat, which are all fundamental, from data acquisition, satellite maneuver, international collaboration, R&D and Calval activities, until the generation and distribution of the nice CryoSat product you are using for your science case studies and in preparation of new and future missions such as the Crystal satellite. So we will start with Tommaso, who will present us an overview paper on 11 years of CryoSat and beyond. So please, Tommaso.
Thank you, Jerome, and thank you, Tanya, and really good afternoon to everyone. And thank you again for sharing your time to this, I would say, very exciting and I would say fantastic conference. I would like to present you the status on the CryoSat mission after 11 years in space, in operations, I would say, with an outlook also for the future. But before moving to the next slide, let me really acknowledge in this sentence under my name all the people that have been working on this mission in the last 11 years, operating the satellite and ground segment almost 24 hours a day, going to different difficult areas to collect data in their campaigns and making sure that the data was always there on time. The data, innovative and new data of high quality, and making sure that you could transform, I would say, this anonymous bits into fantastic results, which you really have shown this week to the community. So let me go to my next slide. I hope this works. So CryoSat, as you all know, was launched 11 years ago on the 8th of April from the Baikonur Cosmodrome just before 2 p.m. UTC. Let's try to recall those moments for a second. So 17 minutes later, we had the first acquisition over the Italian ground station of Malindi in Kenya. 4 days later, we acquired the first radar signal over Kiruna, Sweden, and then went through 6 months of commissioning that was led by Richard and by Robert Cullen. And since then, I will say the satellite has and its instrument have worked really remarkably well. CryoSat really has been revolutionary in many ways, and this has come out of many presentations this week. The launch was not a conventional one. It was not from a surface launch pad, but the satellite was put atop a Dimiep rocket, which emerged from an underground silo. The orbit was and is different from any other Earth observation satellite. CryoSat, as you know, is flying in a non-synchronous orbit with drifting ground tracks, with a high repeat cycle. And now we have with no repeat cycle after the recent orbit change to be resonant aligned with ISAT. Although we have maintained some important subcycles and retained the capability, of course, to reach 88 north and south latitudes. The CryoSat instrument was also revolutionary at that time. It's therefore not a conventional pulse-limited altimeter, but a first delayed Doppler altimeter with an interferometer capability, which we have seen this week, what have brought to science with SWAF, whose technology and the scientific results will pave the way, certainly for future missions, have paved the way, then will pave the way to future missions like Sentinel-3, Sentinel-6, and Crystal. The mission, as you know, was primarily designed to determine regional and basin trends of the Arctic sea ice and to determine regional and total contribution of global sea level rise due to the Antarctic and Greenland ice sheet melting. Both objectives were and still are important to understand how global warming is affecting our planet cryosphere, which, as we all know, will impact our future society. In terms of mission requirements, the objectives translated into inaccuracies of measurements over certain ice fields, and you have seen this table many times. And all this was achieved in the first 3 years of CryoSat lifetime. Then the mission has been extended 3 times, and currently we have funds to operate the mission until 2022. And in the discussion of the last extension, which was in 2019, after having demonstrated that we were still fulfilling its prime and secondary objectives, plus and securing, very importantly, the long-term data record, plus a number of additional goals and criteria which are set by the procedure authorized, set by the member state, it became clear that also thanks to CryoSat, that new stimulating, I would say, scientific questions had emerged that required, in our view, some attention. For example, a full updated knowledge of the snow load at global and local regional scale in the Arctic was and is still missing. This, as you know, is particularly important since the whole region is changing because of global warming, and its affect not only the retrieval of sea ice thickness, but also the water fresh circulation over there. And for example, a complete characterization of the polar oceanography in a changing environment was still not complete. And we have seen yesterday the talk from Camille, how this is really complicated to do. So with this in mind, we proceed in 2019 with a number of objectives, which you see in this slide, which cover different areas, so that the key arguments for extending the mission until 2022 and beyond were there, not only to sustain the long time series of a unique climate record of the full cryosphere, because this is our main goal, but also to present attractive scientific and technical objectives, I will say, that look also into taking consideration as well a continuous dialogue with the scientific community, which we're having in these workshops, and also open new questions, as I mentioned before. And all these were, I will say, put into 7 new objectives. These objectives are obviously goals which can only be achieved in a time span of many years. And now they have become the strategic goals of the mission in its 2nd decade of operational life. And just a quick slide to tell you that these objectives have triggered a number of projects, some of which are currently ongoing, which have been primarily designed to achieve those objectives. This is to say that whatever we are doing today since then, and whatever we're going to do into the future, including the evolution of core products, the releasing of new ones, new campaigns, and even the orbit change, had and have the scope to achieve these strategic goals. This year, as you know, we are going through another mission extension process, so that will be and that will be the opportunity to update the ESA member states with the status of those objectives, after having again approved that we are fit space and ground segment to continue operation until 2025. And this is the work we are really carrying on in these months, I will say. Let me give you a quick status on the space and ground segment. So overall, the satellite is in good condition after 11 years in space. The performance of all platform subsystems is better than expected, including the most important lifetime elements. And Giuseppe, which comes after me, will give you a bit more information about that. The power distribution control unit is not on A side, is on B side, and still some redundancy is left on the A. And we have been, as you know, in this situation since October 2013. And recently also the mass memory formatting unit has been swapped to the B side to reduce here the operational load as a result of the fact that we are getting too many errors on the unit, and this was found to be correlated with temperature. Also here we have the prime unit full available. The overall temperature of the satellite has increased by 5 degrees. This, of course, is not the result of global warming, but a clear sign that the satellite is becoming old. And we have discovered an issue related to fuel leakage, and this was already discovered in 2016. The root cause is understood. We are ready to switch to the redundant side at any time, but this will be done for very good reasons in May 2023. And this will give us enough fuel to operate the mission, the satellite, until the last years of this decade. Instrument is in excellent conditions. The degradation is within expectations, and all redundancies are still available. And of course, to prepare for the known unknowns, we are currently reviewing and updating the procedure to switch to Spiral B in case of need. In other words, there's no limiting factors of the space segment to operate until 2025. The ground segment is functioning well with no major issues since launch. The product portfolio is continuously evolving, taking into consideration new demands, novel application, the new objectives, including the NRT needs for operation use, and the number of products, if you look at this clock on your right, generated by the ground segment has doubled since launch with a dedicated ice and ocean chain now. Now the focus in the next years are to comply to the objectives and to the generation of the AOLIS, the SWOT processing products, and what we call thematic. We are disseminating around 50 gigabytes per day, and we are fit also here to continue operation until 2025. Now, it is always difficult to put in one or two slides which major contribution has CryoSat brought to science, and most of them have clearly stemmed out during the conference with excellent talks, I will say. So I will not go there. And again, I would like to thank you for the quality of the presentations which we have seen so far. Here, I just want to say that the focus of CryoSat has always been on the prime and secondary objectives of the mission, and again, on the importance to contribute and sustain the long-term data record over the cryosphere, linking our data from missions in the past to mission in the futures. And there have been some presentation like the one we saw this morning with Helen, how this has been and is happening. And this we have seen, as I said, we have seen many times during many presentations this week. And thanks also to synergies with other missions, we have been able to better characterize, for example, sea ice. And thanks to innovative methods like SWOT, we have been able to measure with great accuracy the contributions to sea level rise of complex area like glaciers. SWOT, in my view, has extended the mission capability, transforming a one-dimensional measurements along the ground track into a two-dimensional image mode altimeter, and this is really new. The synergies with other missions, of course, will continue in the future, and it's important for the new mission to come like CryoSat. Krista. We have already listened to many presentations outlining the importance of synergy, and we have a session dedicated to this. I think it's tomorrow, and there's an open discussion session which will be led this afternoon by Chris Rapley and Mark Drinkwater. But again, I think this matter will come and will emerge. And to use Walter's metaphor about the camel, we let the nose of the ocean come and to look inside our tent, I will say immediately. And actually many other camels did enter their nose in the tent, and we had tried to welcome them all. And of course, we needed a bigger tent, but we are very happy to have done this. And now, thanks to this big tent, in the last 11 years, the CryoSat mission has evolved from a dedicated ice mission to a multidiscipline mission contributing to different science spheres, even beyond what one would expect from a typical altimetry mission, like the important contribution that CryoSat is giving to science related to Earth's magnetic field. There's a nice presentation which we'll give in later tomorrow by Niels Olsen. All this has been very visible in this conference, in many other workshops as well, in all the studies which have been carried out, and in the article which have been published in the literature. And just looking at the impact in terms of statistics and how many publications have been published with CryoSat, well, there has been, as you see on my left, an increased trend of publications since launch. In the first 5 years of the mission, on average, we had an article published every week. These are peer-reviewed articles. In the second part of this has increased to about 1.5 papers per week. The numbers are here related, as I said, to peer review articles. If we also consider other types of publication, then these numbers only represent 70% of the entire collection. The affiliation of the authors by country reports that colleagues from US, UK and Germany and China are the most productive ones, but that 2/3 of the papers are written by European scientists. And in order to deliver data of high quality, we have been relying on a number of special calibration operations that we perform periodically with the transponders, for example, and on the validation campaigns, which we have been carrying out since the mission was conceived at the beginning of century. Overall, we have accumulated more than 20 campaigns, both in the Arctic and Antarctic, using a handful of instruments, flying aircrafts, helicopters, with the support of ground measurements in very harsh conditions. Yesterday, you saw the nice presentation from René, which gave it on behalf of Henriette and gave us a bit more details of what I'm saying here. This has been possible. This is another important element. Has been possible thanks to the collaboration of national and international entities. The focus of the next campaigns now will be to validate the Cryo-2Ice, which now takes me to my next slide. So the idea to combine laser and radar measurements goes back to the time when ISAT-1 and CryoSat-1 were conceived, and that was already at the end of last century. And for a number of reasons, this has not been possible. Now, if you remember, around 4 years ago, we proposed the idea to align the two measurements over extended ground tracks, so not only over cross points. The idea was shown for the first time at the Cryos conference in Banff. And after listening to the feedback of the scientific community, which was not unanimous at that time for very good reasons, we started to define a scenario and resolve all pending questions and concerns so that we were ready for an orbit change in 2020. And despite the problems related to the virus, this was accomplished last July. There is a poster prepared by Javier Sanchez, who is the flight dynamics engineer that designed the new orbit. I really encourage you to visit that. In synthesis, CryoSat-2 semi-major axis was raised by almost 900 meters so that the CryoSat orbit could resonate every 19 orbit with ISAT-2, namely every 1.3 days of an area which can be configured. And of course, we chose that the first area would be the North Pole. And in this new orbit configuration, it increases the duration of the footprint, overlaps between the two satellites, and reduces the difference in time between observations, especially important for CIs with no consequences, and this is important, with no consequences on long-term climate data record. This was an important precondition that was assessed by an expert group. Overall, as we know, it offers a unique and probably unrepeatable possibility to have coincidence, laser and radar altimetry data over polar areas, which are key to understand climate change and will give benefit to a handful of scientific domains, including polar oceanography. I don't need here to mention all of them. And the first results were already shown during this week, and they are very encouraging. The next steps is dedicated, as I said, CalVal campaign to maximize scientific return. We possibly will rephase the orbit of CryoSat next year to maximize Antarctica measurements. And then we are looking forward for the science workshop. So I'm getting almost to the end of the presentation. Let me give you some information about the schedule, the timeline of the next year. The mission has funds until the end of 2022. In the next 2 years, a number of important releases of the core products and their reprocessing will take place. In addition to this, we have also consolidated main milestones of the Aeolis and Tempra products, which are fundamental, as I said, for achieving the strategic objectives. We will complete another mission extension review, which foresees to go through the scientific assessment this fall, and then with ACEO, and then if PBO authorizes at the beginning of next year, we will have funds that will allow us to extend the mission until 2025. We are planning 2 important campaigns, one in the Arctic and one in the Antarctic. And if the Antarctic campaign is confirmed this fall, we will change the orbit phasing in June 2022 to maximize the South Pole measurement. And then we'll go back to the Arctic in spring 2023. We are planning to go to the redundant reaction control system in May 2023 to stop the leakage, hopefully to stop the leakage and allow the satellite to have enough fuel to operate for, we'll say, another 5 or 6 years. We are planning to organize an important science workshop in 2023, but don't forget that next year we have a Living Planet conference in May, which is in Bonn, and then we have a number of important workshops and conferences which take place in the following, I'll say, 2 years. Now, this is my last, almost last, I will say, slide, and just
Tommaso,
to
apologize, you have 1 more minute.
I have 1 more minute. Okay, what I will do, I will go very quick. Actually, I will not go very quick through this because I've said most of it. But what I want to do, I want to show you a small video because you all know that CryoSat is not only about science and technology, but it's also about people. And we have seen many photos already. I had prepared already my personal version, looking at the archive of the photos, and made a small video, which is only 1.5 minutes. This is, of course, is not a complete acknowledgement to all the people who have worked and connected to the mission in the last 10, 20 years. And for this reason, I have an idea at the end. So let's see if the video, it's working. I can see on my third, probably is a bit.
It's working.
Okay. The framing is not perfect, of course, through WebEx. It's just really to say thank you to all of you. And what kind of question is this? You've been disturbing Duncan. We're getting to the end. So if you have not seen yourself in those photos, I'm sorry, but you have a chance, if you wish, to send your photos to the event organization email by the 30th of June, and I will put your photos in this video, and then we will give it to everyone at the end. Thank you very much, and apologize if I used more minutes than I expected.
Thank you, Tom, so much, Tommaso. There is no questions, but I also wanted to take this opportunity to actually thank you, because we've been thanking a lot of people who've made this mission the success it is today, but you are also, in your dedication to this mission, I also wanted to thank you for that. So hopefully many years, you still have quite a few years ahead of you. So I think we should move on then to the next speaker, which is Giuseppe Albini, who also, Giuseppe is going to talk about the 10 years of CryoSat 2 operations. And Giuseppe is coming to us from the spacecraft operations in ESOC, also a group that we wanted to praise them ourselves as well, since they also have been key in the success of this mission, and who sometimes we don't probably acknowledge as much as we should. So Giuseppe, please go ahead, and you have the floor.
So hi everybody, and good morning or good afternoon. Here is the afternoon in Germany. The title of this presentation is Aging with Grace. It was 10 years of CryoSat 2 flight operations, but obviously it was changed to 11 years of CryoSat 2 flight operation because of what we know already. And it's going to be a broad talk about what we have been doing during these years operating the ground operation segment at the flight operation segment of FOSS in Darmstadt at ESOC, for taking care of our beloved CryoSat 2. In particular, the outlook of this presentation, so we are going to see a few figures about CryoSat then and now, and an historical timeline of the major activities we are being performing with the space segment and the ground segment since launch in 2010 until now. And then it's going to be divided in two main segments. The major part is the highlights on the space segment, and then the ground segment. In particular, on the space segment, we will see what were the main operations and special operations we have been doing with the satellite, with particular emphasis on the Star Trackers operation and a big patching adventure of the of the star trackers on board CryoSat 2 that let the satellite and operation and the overall functionality be what you see now. And an history of the collision avoidance maneuver we've been performing to keep us safe from collision with the debris. And then the story of the ESA-2 rephasing orbit. So a summer of maneuver, because it was last summer during COVID time, we performed this major maneuver campaign. And then some hints on the aging, in particular on the MAFU side, and the history of switching to the backup unit. It was touched by Tommaso just before, and some new potential science that somebody is doing about using the magnetometers of CryoSat 2 or making science. And then highlight on the ground segment. In particular, a responsible teenager, why? Why? Because we are 11 years old, and we have been passing more than 4,000 mission days and almost 60,000 orbits and 50,000 ground station passes, 99% of which, more than 99% of which were successful, and the only minority of the lost passes were for ground station issues, or not issues on the satellite itself. We are still a robust space segment, so we are still on the A side of the onboard computer. The MFU-B is on the B side, but just we will see why, because MFU-A is still on the backup and is working. And our payload, so Cyral and the Doris navigation system, are operational on the A side, basically since launch. And we are still an evolving ground operation segment, because we are using a new station compared to the baseline. We are using new hardware and software for operation, because our ground systems are evolving and our teams are evolving. Aging with grace, why? Because we are also helping other missions in performing basic operations activities. For example, we are offering CryoSat for performing tracking campaign and validating ground system. We have been introduced first at ESOC, a streamlined version of the collision avoidance maneuvers. That's why we are aging with our hardware, but we are also an example for other missions. And this is also demonstrated by the solidity of our hardware and our mission extensions. So on historical timeline, here you see what are the main dates since launch to now. We can spot the major activities. The Cyral B, for example, was tested right during commissioning phase. Then we see the start of the routine phase in at the end of 2010 and 2011 at its full speed. The first roll campaign in 2012 to calibrate the interferometer by rolling the satellite, and then some issues also, the PCDU-A failure in 2014 and the activation of PCDU-B, and the Star Tracker patching activities. We will be back on this topic in a few minutes. Some other like funny anomalies, if you wish, like a Cyral alarm mode that was happening from time to time perfectly over Kabul in Afghanistan, probably due to jamming that caused us some headache, and now is over. And then the beauty of the ESA-2 maneuvering campaign performed in 2020, and our last activity on the mass memory, and we are ready for next mission extensions and operate satellite in the future. So the main activities that we have been doing, as I presented in the last slides, are not the only ones that are. We have also some special operations that we perform regularly to take care of the satellite, that are basic one to more challenging one, like Star Tracker selection sequence change and battery end of charge management to extend the battery lifetime, orbit control maneuver to keep our ground track in our deadband and be compliant with the reference orbit, the interferometer roll calibration campaign that we perform once a year, and then other activities like collision avoidance maneuver and transponder passes. All in all, we can see more than 150 maneuvers in space since launch, between maneuvers and collision avoidance maneuver, like 245 Star Tracker images, and more than 700 special operation requests to formalize all these activities that goes beyond the nominal operation that is basically automated. As you can see, one of the activities we perform is the maintenance of the software, of the onboard software, of the systems, of the onboard computer, star tracker, doors, and so on. Here you can see what were the main activities on the software patching domain, starting from, let's say, after launch till recent times. In particular, I want to get the attention on the patching of some components even right after launch, or in the first months after launch, like in the MMFU-A or extensive Cyril-A patch on the application software in 2013, but mainly on the Star Tracker, in particular on the initial acquisition software patch that was performed in 2014, and then a couple of years were needed to fully patch the 3 Star Tracker units between 15 and 16. I will get back here. And lately on the mass memory B, but we will see also in the next slide what this meant. On the Star Tracker, this was a real game changer. I like to see it this way, because due to some losses of attitude on the Star Tracker side, not on the satellite side, due to the high solar activity and South Atlantic anomaly crossing, and in fact, a progressive reduction of the performances at high temperature of the Star Tracker, due to the noise, we had this loss of attitude of the Star Trackers. And so a need of a software patch to deal with this problem arose in starting 2013. If no software patch was performed, the risk was basically the loss of the attitude in some periods of the year where the temperature of the Star Tracker units was rising above, let's say, 15 degrees and so on. And this was tackled by performing 2 major patches. The first patch of the initial acquisition software to make this part of the software more robust, completed by April 2014. And then the second part to patch the attitude update software that is really tracking the stars and providing us attitude determination at all times. This particular one was very demanding in terms of what was changed at software level and how much effort needed to be tested, validated, uplinked, and verified. And here you see below what was the flow of the activities, starting from the algorithm that was developed by Terma and tested by Airbus Defence and Space, and then converted at ESOC, uplinked by us, and verified in orbit. Now, verifying software in orbit on a unit that is supposed to be operational at all time, like the Star Trackers, because otherwise we are ending up in course pointing mode, is difficult because you have to plan it very well. And in this particular case, we used the Star Tracker that was not used at a precise moment and in a precise, let's say, season, if you wish, because it was kind of permanently blinded by the sun due to our structure of our and the movement of our orbital plane with respect to the sun. And basically, we divided the main activity into 5 operational batches that lasted from November 15 to September 16. And with 40 days of operations, we managed to uplink and test and verify the software on the 3 Star Trackers with more than 13,000 telecommands. This was quite remarkable. So I will speed up, then see some aspect of the collision avoidance maneuver. You see that our orbit, our CryoSat orbit, is kind of crowded, and we are facing some collision warnings from time to time from active satellites and defunct satellites and debris in general. And our friend, the Space Debris Office of ESOC, is so kind to check those collision warnings for us and warning us when we need to perform, and we need to discuss whether to perform or not a maneuver. So we get a warning, we call Tommaso, and we start thinking about this. And so the flow of the action is basically can be seen in this slide. So first there is an assessment of the collision risk. Then there is a decision based on the evidence of what information we have. And if the maneuver if the risk is confirmed, we have to uplink a prepared orbit control maneuver. We need to have this maneuver screened and then to execute it and check the execution. Now you can see that we received quite a number of collision warnings since launch, 126, that's quite high number, and 50 were really discussed in dedicated countless meetings, and at the end 16 maneuvers were executed, and a few more were delayed or modified because we advanced, for example, or we changed the timing of a already planned orbit control maneuver just to counteract a debris and so on. So these was quite demanding activities, and believe it or not, at every either Christmas or Easter we receive a notification of this object, and it's not Santa Claus. What was is nice to talk about, and this was touched already by Tommaso before, was the adventure of last summer, if you wish, when we changed our orbit slightly to improve the CI estimate in joint operation with the ESA-2, to try to get in the condition to increase what is the possibility to perform joint science with the NASA mission. The ESA Flight Dynamics group, after the input from Tommaso since 4 years ago, started to study the problem and ended up with this 1920 resonant orbit concept. So by performing this set of maneuvers and raising the semi-major axis by more or less 0.887 kilometers, increasing the opportunity for combined observation by having a 19th revolution of CryoSat every 20th revolution of ISAT, and having a common, if you wish, ground track at this specific time without affecting the long time series. And so after more than 3 years, countless meetings, and 3 weeks maneuver campaign, we managed to perform this orbit raise, and now we are in this configuration. In particular, what I want to present in this slide is this the flow of actions that we carried out in summer 2020, since in the second half of July, starting from a test maneuver with the 5 centimeter per second delta V, and then the 3 batches of 4 burns, so 4 mini maneuvers each batch in 3 different weeks that performed the major part of the orbital raise, and then a touch-up maneuver. Then obviously nothing goes fully according to plan, and you see in the red box a collision warning that we received in the for the 1st of August, time of closest approach. So we had to change the timing of the already planned touch-up maneuver just to keep us safe from a debris and ending up in our final orbit close by in terms of repetition with our with NASA friend. This was clearly a challenging operation because it's the first time we were performing batches of maneuver. It was a complex activity, especially because it was coordinated mainly and mostly from home, and was really important to contribute this with a total of 14 maneuvers and half a kilo of nitrogen used. And in particular, I can underline that this entire set of maneuver, only 23 hours of siral data was lost due to the payload unavailability during the maneuvers, and this was quite good. Aging and redundancy, the case of the mass memory. Why? Because since a few years, the mass memory alpha was experiencing some anomalies that did not really affect the data, but forced us to perform some recoveries. I will not go into the detail of the issues, but the recoveries sometimes were forcing us to recreate the MMFU packet stores. This was quite a consuming operation and included also the need to reboot the Siral instrument, so a science loss every time we were performing this operation. The root cause of this was not identified, but as you can see below, a correlation with the temperature is evident. This could be related to the aging of the unit. So what we decided to go to the backup unit by maintaining the MMFU-A as a redundant unit. So to switch permanently on the B side in April this year, and therefore keep A side as a cold redundant unit. And this was challenging as well because our failure, onboard failure, fault detection and recovery logic considers the backup unit, the B side, always a backup. So without the possibility of being protected in case of issues to be switched automatically to the A side. And so we had to redesign this logic and uplink this design after it was tested, just to have, as we have nowadays, the MMFU-B not only on, but protected in case of issues. And in case of anomalies, we are going automatically on the MMFU-A that is currently off but available. And this is quite important because we are actively using our redundancy and redesigning a bit the failure detection and recovery logic to counteract the aging in a more active way than just waiting the systems become old. One of the last slides I can show you is the use of platform magnetometers data for science. This was started in 2018 with the provision of a data set to our friends at DTU Denmark. And what they end up confirming is that our platform magnetometry data is so good that can be used for science, and in particular to close the gap between the CHAMP mission and the SWARM mission that we have also the honor to operate, and being really a science product they are evaluating. There's going to be a talk about this tomorrow, and so they were also kind of considering us add-on of the SWARM mission, like a SWARM 4. Not only the space segment is aging, but also the ground segment and the flight operation segment. So you can see in the left part in yellow are the components of the FOSS at ESOC that did actually age, and we had to change in both software and hardware level to counteract what is the aging of the ground system, check the software, the new regulations in terms of safety and security, and the new baseline of software, for example, in the use of operation and so on. So we had to, since basically launch all the way through today and beyond, we had to change mission control system version and baseline. We had to migrate to different versions, use of virtual system instead of physical systems. We introduced some interesting notification systems, so we are notified also via SMS in case of there is a big anomaly. For example, overnight, this was introduced a couple of years ago. And we are working on modernizing also our mission planning and again our mission control system again and further to be ready for the next mission extension. As Tommaso was showing in his presentation, yeah, I'm basically over. As Tommaso showed in his video, also this want to be a snapshot of some images that are depicting people working at the flight operation segment in the launch and the early orbit phase and the top phase in the top part of the slide, and another more recent one in the bottom right. And this wants to be and to constitute a big thank you to all the people that were there to operate the systems since launch and mission preparation until now, that maybe now are not working anymore with CryoSat, but they're working at ESA or the other establishments. And wants to be a big thank you to all the people that were really working for continue operating this mission now and beyond until the next extension and further. Thanks a lot.
Thank you very much, Giuseppe. I do not see any question into the chat box. But just, I also would like to thank you, Giuseppe, and FOSS team in general. It is always good to remind and learn a bit more on the dark side of the moon related to the operational task, challenge, and achievement from FOSS in support to CryoSat for more than a decade. So really thank you for this. As most of you know, instrument performance, calibration, and data quality are also key elements for the success of a nurse observation mission such as CryoSat, especially when addressing climate change issue. So please let me now introduce the next two speakers, Michele Scagliola and Stephen Baker, who are respectively in charge of CryoSat Level 1 and Level 2 instrument processing facilities. And we will make a joint presentation about quantifying achievable performance and long-term measurement drift from 10 years of CryoSat data. Please, Michele, the floor is yours.
Good afternoon, everybody. I think that you can see the screen, and this is the presentation talk that will give you an excerpt of the activities that have been performed during these years in the framework of the Expert Support Laboratory. And as just Jerome has said, we will go through in the first part to a brief overview of the calibration activities, in the sense that we will go through the status of the internal calibration of Cyral in long term, and in particular regarding the external calibration, we will give an outlook on the end-to-end calibration of the CryoSat interferometer, which is a key factor to guarantee the interferometric the performance on the angle of arrival accuracy for any interferometric measurement. And then we will, Steve, we will go through the long-term measurement drift from 10 years of CryoSat 2 data from a perspective of the level 2 products. Regarding the Cyral internal calibration monitoring, the important point here in these slides, apart all the list of all the calibration parameters and corrections that are continuously monitored, is that on Cyral there is a complex calibration plan, which is so that the instrument is continuously, at least once a day, is commanded to make some calibration measurements, and then starting from these calibration measurements, the corrections are computed on ground, and these corrections are applied to level 1B products to compensate for instrument inaccuracies and drifts, in order to give to produce level 1B waveform, which are as accurate as possible and compensated for any known inaccuracy coming from the instrument. In particular, you can see here in this slide just an example of Cal1 SAR gain variation internal path delay, and these are continuously monitored. There is a trend from the beginning of mission, but which is under control. I can say under control, and is not affecting the requirement on the instrument specification. And some of these corrections are affected actually also by the temperature of the instrument, which is something that is also increasing as function of time due to the degradation of the insulation of the system. Then we can go to the range impulse response. These are key parameters of the range impulse response quality, like the -TP width, which is linked to the range resolution. And you can see that, as an example, in SAR mode, the range impulse response is stable in terms of range impulse, in terms of range resolution from the beginning of mission. And much more important is that looking at this number here, you can see that we are within the requirements from the beginning, and this parameter are constant, and so the instrument is performing perfectly about this point. Then we have some measurements, corrections from the for the interferometric path, in particular for the AGC phase difference, the Cal4 phase difference. These are also continuously monitored to compensate for the phase difference between the path into the instrument. They have a similar behavior for them because the calibration path is partially overlapped. This is simply mirrored with respect to one, and this is all under control. And we can pass now from the interferometer internal calibration to the interferometer external calibration. End-to-end calibration are continuously performed about once a year with the help of the ESOC, as Giuseppe told before. The in-orbit calibration campaign rolling left and right spacecraft are done about once a year, and these calibration campaigns aims at computing the across-track slope of the ocean surface. And by comparison of by this formula, but the important point is that by comparison of the ocean surface slope, which is measured by the instrument after processing, and the one which is known from an external sources that can be the MSS or the geoid, it is possible to compute an error on angle of arrival with respect to the geoid slope in this case. And starting from this, it is possible to compute an interferometer calibration function as function of the angle of arrival. And in particular, we can see here this term, key zero, which can be addressed to the roll bias. And starting from this calibration function, we can go back applying this calibration function to the interferometer measurements from level 1B products, and we can compute this way the residual error on the angle of arrival after calibration. And this way we can compute the statistic of this residual error and compare with the system requirements on angle of arrival which were given to the mission. So in particular, a residual post-stack accuracy minus that 141 microrad, and the residual post-stack precision at 1 Hz minus that 60 microrad. And you can see here that from on any of these roll calibration campaign, the performance of the CryoSat interferometer in sense of both accuracy and precision are stable as function of the mission lifetime and are below the requirements. And the important point from the user point of view is that the contribution to high error from the achievable performance on the cross-stack angle of arrival can be quantified of about 1 meter, which is very important, which is relevant, and it's fairly beyond the expectation during the design phase of the instrument. So let me conclude that regarding this part, that internal calibration corrections are stable, continuously monitored, and compensating level B products, and that the end-to-end performance of CryoSat interferometer in sense of accuracy and precision are stable and below the requirements. And this makes possible to have the measurements on the level 2 that Steve will show you.
Thank you. So I hope you can hear me and see my screen now. Thanks, Michaela. As Michaela said, this part of the talk is about looking at, from the point of view of the level 2 data, to examine any measurement drift and attempt to quantify the quality as well. I want to acknowledge my co-authors, the MSSL team who've helped to put this together, and also from ESA. I'll carry that on to the next slide though. So just before going on to the talk, a few people have gone back and mentioned some of the contributing factors to the origins of this mission, and Walter in particular mentioned some of the precursors to CryoSat. And in fact, these two pictures from Chris Rapley, shown earlier by Michelle, were from workshops sponsored by ESA, including altimetry experts from industry as well, looking at the subject of imaging altimeters. And so in many ways, these talks, these workshops contributed to all the ideas that culminated in the CryoSat mission. And there's a lot of old faces, I'm sure you recognise there: Richard, Guido Lavrini, Seymour, John Bamber, Frederic, Chris Rapley, many others. So this talk is using the CryoSat performance monitoring and QA service, which was built by MSSL and run as a service for ESA. The website there is open and available to anybody. And this is where I particularly want to acknowledge the ESA colleagues. So Richard Francis was system manager for CryoSat 1 and then project manager for CryoSat 2. And this is when the ground segment was set up, designed and set up, and that included the performance monitoring element of it, which Richard was very well aware was necessary from his long experience of other altimetry missions. And Pierre Viau was the person in charge of the detail there of setting up the ground segment and commissioning this. And of course, post-launch, Tommaso is the mission manager and has continued to sponsor this service and overseen the changes and improvements to that we've made to it over the years. There are a very large number of parameters you can see on here that potentially can be examined in order to provide the analysis that we want in this project. This is just one example, and what's immediately noticeable is that it's boringly flat, and that's really good evidence that the calibration done at level 1 is doing its job. And so they've calibrated out the trends and drifts that we were looking for. And all you see here is steps which result in baseline evolutions that have occurred over the lifetime of the product. Excuse me. One drift that we have been able to measure from crossover analysis is the time tag bias drift, which you can see here is around about 0.2 microseconds, which is tiny for these missions, and there is a very consistent drift of about 5.4 microseconds per year, and this is consistent across baselines. It doesn't jump when we do a baseline upgrade. If you look at the geographic distribution of the time tag bias errors, what this plot is really telling us is that there appears to be room for a little bit more improvement in the orbit modelling, which could very slightly improve this already small effect. So going back to other parameters, again, this one is crossover mean height difference from 2 retrackers. The land ice retracker is one we built in collaboration with Walter and Remco, and the OCOG is the threshold retracker. So that the land ice retracker is a model fit. So again, this is very flat, no indication of drift, but there are changes related to baseline. And one of the messages from this is that well, there are 2 ways of improving the science that can be got out of level 2 data, and that is to improve the quality of the measurements, but also to improve the quantity of the measurements, give the users more usable results. And that certainly happened here. The OCOG results in baseline D, 46% more than we started with. And for the land ice retracker, it's 14.8% more than we had in the first evolution of the ground segment at the beginning of the mission. Looking at the crossover height difference RMS, so we're still not seeing drift, but there are a couple of more interesting things in this. There is visible in this a slight annual cycle, which is anti-phased in Antarctica compared with Greenland. And we can also see here the Greenland surface melt event that occurred in 2012. And there's a similar one that we're seeing in Antarctica in the summer of 2018. And again, this change here is actually correlated with data from lower latitudes. So it's possible that there's some kind of melt event going on around the fringes of Antarctica, but we haven't looked into that more at this stage. Another way that that the coverage of measurements has been increased at level 2 is a continual increase in the availability of the auxiliary corrections that go into the range correction. The bottom example here is the ionospheric correction, which you can see baseline B, a lot of data missing, baseline C, a number of discrete orbits missing, and baseline D, it's virtually 100%. DEMs have been improved. At the start, we were using the Bamber and Ramp DEMs. These were updated to GIMP for Greenland and Bamber 2009 for Antarctica, and then currently we're using the Helm 2014 DEMs. And this helps in two ways. It helps with the LRM slope correction, and it also helps filter the SAR-in results so that when phase wrap occurs, you get ambiguity. You can detect the ambiguity and reject measurements that probably have phase wrap. There's a poster about this, poster number 52, for those interested in seeing more. Then we can look at sea ice. So improvements again, including SAR-in data in the sea ice computation. At launch, it was only envisaged that we would use SAR over sea ice areas, but then this SAR-in test area was introduced in the Arctic, and for a period of time, then it was switched back. But now we have included that in the freeboard processing chains. And this also has the advantage of including more data near the coastline, which you can see here, northern Canada, and in the North Greenland Sea here, as well as in this missing box. So another example of how coverage has been improved. There are a number of updates going into baseline E, which is coming into operation in the latter part of this year. So from September, that will go online. So further improvements to come. Here are a couple of examples. So from sea ice, we're looking here at the surface height anomaly RMS error. In baseline D, the RMS error was around 5 centimeters. In baseline E, it's around 1.5. So that's a very nice improvement in the accuracy of the surface measurement. And here's an example from land ice. This is a comparison of baseline E elevation data directly against the REMA DEM. And over Lake Vostok, which admittedly is a very well-behaved area, a very nice sort of calibration target, we're getting millimeter differences in the mean and only a few centimeters of in standard deviation with the various retrackers. But this is, of course, something that will vary with slope. So conclusions, the performance is obviously excellent and stable. There really is no visible drift in the level 2 data, and this is thanks to very effective level 1 calibration correction. So thanks, Michaela, for making my talk less interesting than it could have been. We do observe a very small time tag bias. There are clear improvements in measurement accuracy and useful measurement coverage over time, and these are correlated directly with the baseline updates that have been implemented. Land ice range standard deviation is down at centimeter level. The sea ice, the surface height anomaly RMS, this is indicating that surface height retrievable is basically to centimeter level, which means thickness retrievable to 10 centimeter level. And this is all in line with numbers that have come from other people's talks. The mission requirements specification document was mentioned by Michel Samados earlier. And again, this is the benchmark, and what we can really say is that performance exceeds the mission requirements specification. So that really is a lot to celebrate, I would say. That's it. Thank you.
All right. Thank you so much, Steve and Michele. I don't think there's questions, and since we're a bit late as well, we'll move on. There is, however, a comment from Mark that you might check, Steve, since it's directed to you. And so we move on to the next speaker. which is Paolo Cipollini. Paolo has joined ESA a couple of years ago, so well, more than a couple of years, 2018, but he has recently joined the Science Mission Division and became the Crystal mission scientist. And so we're very happy to have him here to introduce the mission and to look also at, give us a status update on it. All right, Paolo, you have the floor.
Thank you very much. Good afternoon to everyone, dear colleagues. I'll just switch off the video as my home broadband is a little bit on the thin side. My slide. So I'm here to present Crystal. It's a beautiful mission that we are planning for the future. And I should really acknowledge the contributors to the design and implementation and science behind the Crystal, the Mission Advisory Group, and a number of ESA colleagues in particular. I'd like just to mention in person Michael Kern, the former Crystal mission scientist, who's put together such a nice group of scientists. He was responsible for running the MAG before myself, and he has collated the mission requirement documents. So thanks very much. Michael has moved to a new position within the agency, and I'm taking over from him now. So Crystal, we are operating in a policy scenario where the EU obviously wants to do some good for the Arctic, recognizing, how sensitive this particular environment is to climate change. This is the EU Arctic policy from 2016, built around 3 pillars, and one very important one for us is the climate change and safeguarding of the Arctic environment. And there have been public consultations on that, and you see the results of the public consultation in that document on the right, issued in January. But one key sentence in the Arctic policy is that we should implement monitoring of climate variables and ice thickness through Copernicus. So you've got this policy scenario, and then you've got what we've seen what we are seeing in this particular conference. We've got the beautiful results from CryoSat and the science that this mission is enabling is taught us really that you can do successfully radar altimetry almost all the way to the poles. It has established SAR mode altimetry for good. Then we have seen fantastic results from the interferometric capabilities. So there's good rationale for keeping these capabilities for the future. And also CryoSat has allowed fully focused SAR processing to be demonstrated. So CryoSat has brought along all these nice contributions to the science revolving around the Earth's radiation budget and the sea level budget, and of course many interesting results also for oceanography and hydrology, as indeed we are seeing. Once you've got this policy scenario and these beautiful results from CryoSat, obviously what you want to do is to continue this in the future and bring it to the next operational level. And here we are. Let me introduce you what we're doing next, which is introducing Crystal, which is going to do exactly that. Take CryoSat's heritage and propagating it in the future in a sustained way, fully operational way. Crystal directly addresses the EU Arctic policy, and there have been user requirements gathered by the sea and expressed in Polar Expert Group reports. I'll get back to those again in a moment. Crystal will be fully operational, so it's a mission with 2 satellites, A and B, covering a relatively longer time frame, certainly more than a decade, we hope, within the Copernicus expansion framework. And it will be the first high-resolution radar altimetry mission for the cryosphere, operational since the design, fully operational since the design phase. It will provide, and these are the primary mission objectives, high-resolution sea ice thickness and snow depth in the polar regions, and high-resolution land ice elevation measurements for Antarctica and Greenland, on the including the margins, including the glaciers, and then of course the ice cap. It will be the only radar altimeter that goes to 88 north after CryoSat 2, and as such, it has attracted a very strong support from the user community. We recognize that we need these kind of measurements, and they're going to make a big societal impact, and also a big scientific impact to the science of climate change in particular. So there's a letter that you will have seen last autumn sent to the AC, stressing the importance and the urgency of this mission. And it's based on the heritage of CryoSat 2, but with some significant improvements. Let me mention them here. So it's interferometric SAR altimetry in the KU channel, but with an additional Ka band channel. So that allows you to a better measurement of the snow depth. The Ka band is non-interferometric, but it brings a definite plus in terms of looking at the snow layer. And then it will have a passive microwave radiometer for not just for the wet tropospheric correction, but we're planning to use it for ice and snow classification in the polar region. And in terms of performance and operation improvements, the bandwidth is improved with respect to Crystal, so we go from 320 MHz to 500 MHz, which improves the range resolution. That is particularly important for measuring the freeboard, for the sea ice freeboard. There's better baseline stability for the antenna plate, leading to improved interferometric measurements. So we expect a 50% improvement on the elevation error from interferometric measurements. And the possibility of doing fully focused SAR processing in particular should lead to a high precision monitoring of iceberg and ice lead discrimination with the higher along track resolution. And finally, we've also added open loop tracking mode to allow proper tracking of glaciers. The key requirements are in this slide, and you can see the main performance and latency requirements, including, I should say, the requirements for the ocean products. And both on the ice surfaces and on the ocean surface, there's a near real time of 3 hours or 6 hour product, and then there's some intermediate time, short time critical in ocean parlance, we would say, of 24 hours and 48 hours, and then there's the non-time critical products. And most of these products are already validated from CryoSat 2, but of course we expect them to be even better with the higher accuracies that I was mentioning in my previous slide. But there will be new products, in particular, look at the one for snow depth and sea ice, and also there will be an iceberg detection within 24 hours. So Crystal is really, in this slide, you see how Crystal is really inserted in the Copernicus framework, how Copernicus collected the polar expert group recommendations in a number of reports. Those are the user requirements for the Copernicus polar mission, and those have inspired the mission requirement documents for Crystal. And the products that we are generating target virtually all the Copernicus services. So from the climate services, contributing to ice projections and sea level rise studies, to CMEMS, the marine services for marine monitoring, marine forecasts, to the land services, of course, all the products dealing with the terrestrial cryosphere, ice sheet and glacier topographies, no depth, are of extreme relevance to those services. Atmospheric services are in particular interested in the snow products, and also the emergency services for things like inundations and the degradation of permafrost. Now let's get a little bit more technical. I will show you briefly with this table some of the main technical characteristics of IRIS crystal altimeter. This is the configuration table that tells you all the different modes of measurement and all the different features of the different surfaces. So over the columns, you go from left to right, the ocean, the sea ice and icebergs, and then on the right, the land ice, including glaciers. And I would first like to highlight that we will have interferometric capability for the KU channel of the ice surfaces. So you see, for sea ice and icebergs and land ice and glaciers, we are in SARIN in KU band. But then look also at the extended range window of a land, which is obviously necessary to follow the topography. It's very important also to notice that we will have an open berth, or if you prefer, you can call it interleaved measurement mode over sea ice and icebergs. One crucial feature which will allow us to track the more rugged topography along the ice margin and in glaciers is the adoption of an open loop tracking mode. In terms of where we are with the project, the space segment industrial organization is in this slide. The full consortium has been established. The contracts have been awarded last autumn, or at the beginning of the autumn, for the space segment development. That would be phase B2 CD. And Airbus is the mission and satellite prime contractor, and Thales Alenia Space is the prime contractor for the instrument, for the altimeter. It's a consortium, of course, that has a large experience in altimetry mission, including on CryoSat 2 and Sentinel-6. But around these two primes, there's a constellation of many companies from different countries with little but significant contribution from SMEs. And we had a couple of months, or 3 months ago, we had a successful system requirement reviews. That's where we are at the moment. So you can see here the timeline for the development of the platform and instrument, or I should say the platforms and instruments, because of course there's Crystal A and Crystal B, and Crystal B will be then, stored for launch later. But for Crystal A, the launch date is at the moment towards the end of 2027. So, in summary, Crystal will be a state-of-the-art altimeter for the cryosphere. Well, of course, I shouldn't say too loudly, but we expect it to be good on the oceans too, and for inland waters. So I really expect that once it's there, like for CryoSat, we will see a number of interesting applications also in the other domain. But it's the first dual band altimeter. And the fact that you've got both bands simultaneous measurements in Ku and Ka over the cryosphere opens a number of new scientific opportunities. We discussed those a few months ago in an interesting workshop. I will report tomorrow morning on this dual band workshop. So come and join my presentation tomorrow if you're interested. Crystal is also highly synergistic with other Copernicus expansion missions over the cryosphere. There's ROSEL, radar, L-band radar, and the SIMR, the microwave radiometer. So we've got an integrated monitoring of the polar regions from altimetry, microwave, passive microwave, and radar, all up at the same time. And we should really give credit to CryoSat and this fantastic mission that we are celebrating in this workshop, because Crystal builds on the success of CryoSat and really brings CryoSat achievements and success up to operational fruition for Copernicus and its services. So that would be the key message from my presentation. Thank you very much.
Thank you very much, Paolo. We have one question comment from Tommaso. If NASA is planning new altimeter mission in the near future, such as LIDAR, as Helen said, would you explore the possibility to have some kind of resonance tandem orbit with them? If LIDAR would have laser, Ku, Ka over some ground tracks, timing of launch and development might be okay, to be checked, of course.
Especially that
Yes,
we have Tom also here. Sorry, Paolo, go ahead.
Yeah, Tanya, yeah, I'll let you comment in a second, but I can only say that we have already started thinking about that. Of course, the opportunities that we're seeing coming now from Cryo2Eyes are so good that in planning this future mission and the timing and the orbits, we will certainly keep the door well open should a similar synergy arise with the future NASA altimeters. It's too good not to be considered.
Okay, and so before we, sorry, Tanya.
No, I agree, and also maybe we let also Tom after Tom's talk, we can also just briefly come to this as well, since he's going to give us status on the ISAT-2, and also he's from NASA, so probably you can even give us more information on these future plans on the NASA side. I just have actually it's a more logistic question for Paolo. Paolo, you said that you're presenting tomorrow, but I was actually looking at the schedule and I don't see a talk assigned to you. When are you going to present?
Exactly, I don't know, but I was told that my poster had been upgraded to a presentation, and I have accepted that, but they haven't told me exactly which slot. So okay, I'm afraid I can't.
So we'll keep an eye for
but
tomorrow.
perhaps Matteo, who's listening to us, can clarify it later.
Yes,
I'm not entirely sure.
Yeah, we can check it offline. No?
Yeah, sorry, the updated program is already on the website.
Oh, thank you.
Okay, thank you, Veronica.
You're welcome.
Thank you, Veronica.
And maybe just
all right.
Yeah, before we move on the next presentation, just a comment from Jérôme Benveniste about good on the ocean too and inland water indeed. For sure, Crystal mission will allow to address a lot of science issue and application over inland water body.
Absolutely. I think I had hydrology in one of my earliest slides. Sorry, but thanks, Jerome, for reminding us. Those missions, by virtue of the SAR capability and the SARIN, have a clear edge with respect to low resolution mode altimetry of the inland water surfaces. So we'll use them for sure.
Okay. All right, so let's move on to Tom. Tom Newman, I think most of you know anyway, but let me introduce him. So he's the project scientist for ISAT-2, and he's coming from us from NASA in Goddard, and he's going to give us an update on the ISAT-2 mission. You have the floor, Tom.
Thanks, Tanya. Presumably you can hear me okay and you can see my slides? Yep.
Perfectly.
Awesome. So yeah, I'm Tom Newman. I am the project scientist, and I'd like to echo something that Tommaso touched on earlier, that these missions do require a village. So while I do have the pleasure of presenting on behalf of the mission, it really is representing the work of many, many people behind the scenes that make these missions possible. Also, at the outset, I wanted to say congratulations to the CryoSat team. We ISAT-2 are obviously the new kids on the block and aspire to have such a 10-year symposium 7 years from now, or maybe 8 if we try to go for 11 years, such as CryoSat-2 is now. So congratulations to all of you. The ISAT-2 mission, of course, is the successor to the original ISAT mission on orbit from 03 to 09. And ISAT-2 grew out of the 2007 Earth Science Decadal Survey. That's the process by which U.S. agencies get their direction for future Earth observations. Similarly, with future LiDAR missions, I can comment a little bit at the end, but they are driven by the 2017 Earth Science Decadal Survey that Helen Fricker was actually a part of writing. ISAT-2, we've been up for almost 3 years now after launching in September 2018. And the purpose of this talk is to give you just a brief mission overview, some data examples and how things are going, as well as the health and status of the observatory in space. In case you hadn't looked at ISAT-2 data before or hadn't thought about it, we are a laser altimeter. ISAT-2 generates a single laser pulse in the green part of the spectrum, and that pulse is split on board to generate 6 individual beams or footprints on the ground. Our beams are arranged in a rectangle pattern as shown over on the right-hand side. And by slightly yawing the spacecraft, we generate 3 pairs of beams on the ground. So the figure on the left is a schematic of how those beams fall on the Earth. Each footprint has an 11-meter diameter. And with the pulse repetition frequency of 10,000 laser shots per second, it generates a footprint on the ground every 70 centimeters along track. So it's very dense along track coverage, but as you can see in the schematic, it's very sparse in the across track direction. The measurement concept detects and times individual photons as they arrive at our detectors. And so it's those individual photon times of flight that are the basis of our elevation measurements. We've been on orbit just over 1,000 days, and it was great to hear that CryoSat-2 is up for, I believe the number was just over 4,000 days, so it's definitely something to aspire to. Our Atlas instrument has been transmitting laser light since shortly after launch, about 2 weeks after launch. And at least as of today, we're up to about 880 billion laser pulses, which is a tremendously large number. Just a few of those stats there, and I'm happy to say that the performance metrics for the Atlas instrument, as well as the observatory, remain nominal and well within requirements as we approach 3 years on orbit. Some examples of what ISAT-2 data looks like. This is a pass over West Central Greenland in summer of 2019. And each one of those dots or points are individual photons detected by ISAT-2. The level 2 product provides a latitude, a longitude, and a height for every photon that's detected. The speckle you see in the background is due to solar photons at the 532 part of the spectrum. But of course, the heavy black line throughout the middle of the figure jumps out at you, and that is the surface return that's composed by many, many thousands or millions of individual photon returns. In this case, we have height on the y-axis, distance on the x-axis expressed in latitude, and you can see the topography of the Greenland ice sheet, as well as some individual melt ponds. There's about 3 of them across the scene. Green laser light penetrates water particularly clear water, and in some cases we get a surface return off the surface of the water, as well as a bathymetric return off of the bottom of the melt pond in this case, and we'll see a few more examples of that. Many of you will be aware of iceberg A78, which calved off the Ronnie Ice Shelf just a few weeks ago. And we had the good fortune to have an ISAT-2 pass shortly after a Sentinel-1A image on this May 18th, rather. And this is the kind of data you can see from ISAT-2. In the lower panel, we again have height on the y-axis and distance on the x-axis. You can see individual crevasses in the ice shelf as we go from right to left. Some melange in the open water between the iceberg and the ice shelf, and then a few tracks over the iceberg itself. This was too good not to share, and it was recently in the news as well. So nearly coincident data between Sentinel-1A and ISAT-2. In addition to collecting data at the poles, our orbit takes us from 88 north to 88 south, as CryoSat-2 does as well. Of course, we also collect data over everywhere in between. And ISAT-2 has been supporting terrestrial ecology studies that are particularly focused on measuring vegetation canopy height as a means to estimate above ground biomass. So the challenge for terrestrial ecologists is to take a photon cloud, such as that top panel on the right, and classify those returns as either a ground return, a canopy top return, or a return from within the canopy. And so those algorithms are led by Amy Neuenschwander at the University of Texas at Austin. And they provide a really nice complement to the JEDI laser altimeter. JEDI is perched on the International Space Station, so only gets up to 50 north and 50 south. So ISAT-2 is a nice complement in that it extends farther to the north. In terms of land ice science, the main goal of ISAT-2 is to measure ice sheet change, of course. And this was our first paper using ISAT-2 data at a large scale and combining it with data from the original ISAT mission to reveal changes in the shape and the volume of the Antarctic ice sheet in this case, in the figure on the right, by using firn models that allow you to convert from a volume change to a mass change. We're then able to estimate mass changes in the Greenland and Antarctic ice sheets. Of course, that's familiar to many of you here on this call that have been using CryoSat data to do that for many years. I had mentioned melt ponds earlier, and here's a few examples by colleagues, both over sea ice in the lower left, a paper led by Sinead Farrell and her colleagues, as well as over land ice in the figures on the right in a paper led by Helen Fricker and colleagues, looking at melt pond bathymetry and geometry by combining imagery and ISAT-2 elevation and bathymetric data over the Amory ice shelf over on the right-hand side, and then Sinead's example here in the Arctic Ocean as well. Bathymetric returns and melt pond detection wasn't a primary science driver for ISAT-2, although once we were on orbit and we in the science team recognized that ISAT-2 will do a really nice job in lots of cases of measuring that bathymetry. Sinead and others have worked towards developing algorithms that will automatically detect and measure melt pond bathymetry. So this is a case perhaps of the camel sticking his or her nose into the tent. We can do interesting things for melt ponds, and then the rest of the camel will follow, and hopefully we will end up with melt pond algorithms and data products in the future. Over sea ice, ISAT-2 data allows us to monitor the sea ice growth, as CryoSat-2 does as well. Our time series, of course, begins in October 2018, so this series of monthly maps of sea ice freeboard in the Arctic Ocean span October 2018 through the March of 2019. And this was a paper led by Ron Kwok and others. Of course, by combining that freeboard data with models for snow accumulation and redistribution, one can convert sea ice freeboard into sea ice thickness. And these are some example plots by Alec Petty and colleagues, again showing November 2018 through early 2019 as the sea ice grew during the Northern Hemisphere winter. Over the world's oceans, ISAT-2 with its very small footprints and high rep rate in clear sky conditions does measure ocean topography, as shown on the left figure, a monthly map for November 2019. However, drilling into any particular pass, as long as the laser light is able to reach the surface, ISAT-2 is able to measure individual swells and wave structure of the ocean, which is super cool. So that's a large, relatively untapped field. Those products are led by Jamie Morrison and colleagues, but I suspect we've only scratched the surface of what ISAT-2 can do for ocean topography. In a recent paper in GRL just a few months ago, authors compared ISAT-2 gridded data from our ATL-12 sea ice height product and looked at global sea level change and compared it with the standard JSON-3 data products. And what the authors found is that ISAT-2 compares very well with radar altimeters when looked at on a global scale over the global oceans, and that have a mean residual there of around 3 centimeters plus or minus just a few tenths of a millimeter per year in sea level change. These authors concluded that as ISAT-2 data accumulates over time, it would be well worthwhile including ISAT-2 data in global estimates of sea level rise. One of the advantages of ISAT-2 is that the small footprint of ISAT-2 allows us to get sea level measurements very close to the coast, which would extend the reach of many of these models to be much closer to the coast than is possible through the large footprint radar altimeters. I had mentioned bathymetry before, at least over melt ponds. Here's a few examples over. This is over the Caribbean. And so if ocean water is relatively clear and not turbid, we also can measure bathymetry, and that's of interest to lots of different organizations, not only for scientific purposes, but also for navigation. ISAT-2 data can measure shallow water bathymetry, which is a challenge in lots of places. And so this is another example of future work and future data products as the science team and science community works towards automated bathymetry detection and measurement. And of course, I'd be remiss if I didn't mention Cryo2Ice. This is a really fantastic tool, and if you haven't tried it, I really encourage it. And kudos to the ESA CryoSat 2 team that put this together. It allows users to look for data overlaps between ISAT 2 and CryoSat 2, yes, but they've also now added Operation Icebridge airborne data, and it really makes it easy to find these segments of data overlap between your two favorite measurements. Folks have started using this, the data from the Cryo2Ice campaign, to look at differences and comparisons between CryoSat 2 and ISAT 2. This is a figure from a paper led by Stephen Fons that used their algorithm that takes CryoSat 2 data and attempts to measure the snow-free board from CryoSat 2 with some clever retracking and compare it with the snow-free board measured by ISAT 2. And they find they compare very favorably here in the Antarctic and the Southern Ocean. Another example from Marco Bagnardi and colleagues that Marco had a poster rather, on yesterday, comparing CryoSat 2 and ISAT 2 sea surface height anomalies in the Arctic Ocean. ISAT 2 has the 6 individual beams, and over time we have gradually and incrementally improved the agreement, the absolute agreement between height measurements of those beams. Here, Marco and colleagues focused on ISAT 2 beam 3, which is generally regarded as the best one. And you can see the statistics here with the histogram in the lower right, comparing sea surface height anomaly from the two missions and showing a mean difference of 0 centimeters and a standard deviation of just 6 centimeters, which is really encouraging. Common question is how good are our ISAT 2 data? We saw some really good presentations earlier today on the CryoSat 2 data. In the interest of time, I just have one slide or two. One of our main calibration sites is the 88 south line of latitude, where Kelly Brunt and colleagues have measured independently measured the ice sheet topography using high precision GPS along the traverse shown in the lower left. And by continually comparing ISAT-2 data against those GPS measurements, she and colleagues have shown that the individual photon data in that region anyway is accurate to around 5 centimeters with about 13 centimeters of scatter around that. And as we move to higher level data products that aggregate those photons together to improve the accuracy just through data aggregation, the ATL06 land ice product is good to about 3 centimeters vertically, and the precision correspondingly improves as well. The other tool we often use are corner cube retroreflectors. The central figure there has a small piece of glass embedded in the center of that plastic cap that reflects 532 nanometer light very, very well. And some of those returns are shown in the figure over on the right. So we survey the locations of those retroreflectors on the pole with GPS, and then compare them with where ISAT-2 data thinks those corner cube retroreflectors are. And we use that as a measure of the geolocation accuracy. We recently produced and released release 4 of the ISAT-2 standard data products, and using a network of these corner cube retroreflectors, both in the southern hemisphere and in the north, the horizontal or geolocation accuracy of the data is good to around 4 meters, which is really encouraging. And it also reveals that our footprint diameter is about 11 meters or just over. And that's a paper led by Lori Magruder and colleagues that recently appeared in Earth and Space Sciences Journal. The ultimate accuracy really does depend on your particular terrain. As we heard earlier, rougher terrain or vegetation or atmospheric conditions can degrade that. So you can consider the, in many respects, the 88 South results as a best case scenario. Anywhere else you look on the planet, it's typically more challenging conditions, and you'll see a corresponding degradation in the ultimate accuracy and precision of the ISAT-2 photon data. But in those cases where we have a bright reflective surface that's reasonably flat, such as at 88 South in Antarctica, we get height accuracies better than 10 centimeters, in some cases much better, and geolocation accuracy better than 5 meters, and in many cases down to about 3.5 meters. ISAT-2 is in a repeat orbit, so we do attempt to illuminate the same tracks on the ice sheet over and over again. And for the polar regions where we are in repeat pointing, we try to hit the same track again and again. Our performance on repeat pointing is about plus or minus 10 meters. You do see a small wandering of the beams. They wander at about the same scale as the footprint diameter. When we attempt to off-point to other targets, the example I use all the time is we point to my mom's house. We don't actually, but if we're pointing at a target, we see a little worse pointing control because we're rolling the spacecraft to attempt to hit a specific latitude and longitude. And in that case, our control is about 45 meters. Our data products are served through the National Snow and Ice Data Center.
2 minutes.
Thank you. I'm just about there. Our data products went live in May of what year is it now? This is 2021. So they went live in 2019, May of 2019. And some 13 million files downloaded so far that include higher level products for sea ice, for land ice, for ocean, inland water, as well as land elevation and canopy height. Also served through the NSIDC DAC are a variety of tools to help you with data discovery and getting started with the data products, so you don't have to start from scratch. The goal is to allow people to get up to speed reasonably quickly with any of these data products. And users and the science team continue to develop and contribute to those tools. I mentioned earlier that the ISAT-2 observatory remains healthy. One of the questions we often get is about the propellant we have remaining for orbit keeping. Our prime mission was 3 years and 60 days, and that ends this year in December of 2021. But we have fuel to last much longer. We'll go through hopefully a series of mission extension reviews, very similar to the CryoSat-2 experience. And assuming assuming the mission extensions are approved, based on current estimates, we have fuel for station keeping for approximately 9 more years. Of course, that depends on things like space weather, as well as the attitude and control systems continuing to behave well nominally, not having fuel leaks and that sort of thing. I often say that we're just sort of one bad day away or one space rock collision away from ending the whole thing. But so far, knock on wood, everything's going well, and we have propellant for many years of orbit keeping to come. And this is my last slide. It kind of recaps some of the things you've already heard. There are about 80 science papers already in print, many more in review. And yeah, all is well with ISAT-2 up in space. Perhaps if I have just 30 seconds left, I'd comment on the next LiDAR mission. Of course, we hope ISAT-2 and CryoSat-2 continue for many years. The 2017 Earth Science Decadal Survey called for ice topographic measurements as part of the Earth System Explorer category of missions. That is a group of competed missions, and the Decadal Survey called for ice topography as one of 7 different science areas to be competed through a proposal process. We, of course, have been watching for progress in the Earth System Explorers class of missions, and we expect the call for proposals for those missions to come out sometime in the next year or so, and the proposal process will begin from there. And yeah, we'll see how that develops. We certainly intend to propose an ice altimetry mission using laser, and I would be happy to talk with folks about coordinating between laser and radar measurements, since we've seen such great success from the Cryo to Ice campaign, as well as many aircraft campaigns that demonstrate the fantastic science that can be achieved by combining laser and radar measurements together. And maybe I'll pause there and take any questions folks have.
Perfect. Thank you very much, Tom. You already replied to the question I intended to ask you about the future of ICE mission from NASA side. Maybe just regarding potential campaign and OIB follow-on, you have some plan in mind for the close future?
Yes, I suspect that there will be many proposals submitted in response to that call for proposals. The concept that we're working on with many members of the ISAT-2 team calls for a relatively simple laser altimeter using infrared laser light and full waveform digitization, more similar to the ISAT mission than the ISAT-2 mission. That's driven in part by cost. The Decadal Survey called for a cost cap of these missions, which would preclude us from doing a large, more complicated instrument such as we use on ISAT-2, and to get smaller and faster, leaner and meaner, better, faster, cheaper kind of logic. So we'll see what the language in the call for proposals looks like, but that's our current concept anyway.
Okay, perfect. Thank you very much, Tom. There is a cosmetic question from Tom in the chat. I guess you can directly reply in the chat box. And I think with that, we can maybe close the session. I don't know if Tanya has some additional question or comment.
No, I think Tom answered all the questions that I had as well, and that also were raised this morning with Andy toward that he asked Alan in the morning as well. All right. I would also say these were really great talks as always. The meeting continues with the outstanding presentations, and we should move on to the break. I think we're a bit behind, but not too much. I think we still have time for at least a coffee break.
10 minutes,
and
yeah,
then,
a big coffee.
Yeah, and then we move on to the next session. This is to say that tomorrow morning there will be the second session on synergies with the EO missions as well. So don't forget to attend that as well. So thank you to all the speakers. It was really great having you here, and see you later.
Thank you very much. Have a nice coffee break.
Bye-bye.